So raise your hand if you know what CHIP-8 is. Yes. You lying. I know. No, I know you're not. I know you're not. So first of all, let's go with the introduction if this thing helps me. So, but in the spare time, I also do work at Microsoft. I'm on Dynamics 365 right now. I've never used it before. So one thing that I have to say is that everything I'm gonna say today is not associated with my company. So opinions are my own. Okay, I said that. That's it. Anyway, so today we're gonna talk about emulators, what they are, why we need them, because we do actually need them. There's a couple of scenarios why we want an emulation. So there is a tiny difference between emulation and simulation. So with simulation, you're very, very, very correct. You're simulating the behavior of a different system via software, but you don't care about the hardware. Okay, you don't care at all about the hardware. And bear with me, it can be literally anything. Like if you ever played racing game, like Formula 1, or I like Forza Motorsport on the Xbox, for example, that's a simulation. You're simulating what will happen if you crash your car, more or less. While instead, when you're emulating, you're trying as hard as possible to make the hardware work virtually. So that's tiny different, but makes a lot of difference actually internally. So why would we work or build on an emulator? First of all, it's a very good learning exercise if you want to know how things actually work. AI is abstracting a lot of stuff from us. Okay, you read a prompt and poof, magically works, but you don't know how the bits are being sent over the wire or why they actually mean anything for you. So with an emulator, you will learn about memory layouts, CPUs, registers, instruction sets. Yes, thank you. Thank you. Second thing, reverse engineering and preservation. I like the second part. It's very important. Who owned Game Boy? Do you know what a Game Boy? Okay, fantastic. Can you find Game Boy video games right now, cartridge? Yeah, the cartridge, the physical ones.
I don't know, but online you can find them online.
Online, but I'm sure that you have to search for them quite a lot. I mean, you have to dig, but if you grew up with, say that again? They're not produced anymore. I mean, even CD-ROMs, well, DVD for the Nintendo Wii, they're not sold anymore. Okay, so what if you desperately want to play Tetris on a Game Boy? Why would you? But if you want, you can't. So that's just an example, but there's a long list of hardware pieces that are not available anymore, and the software that was running on those hardware is not available anymore. So what do? You write an emulator, and you can also store and save those pieces of software, those pieces of history, in a museum, for example. Another thing is performance experimentation. Let's imagine that you are tasked, because that's your job, to build a piece of hardware, like an actual CPU or anything. Are you actually going through the process of creating it from scratch and having the physical CPU in front of you every single time? How many times do you press, I don't know, F5, you run your program, and oh my God, it's not working, let me go back. Imagine of doing this for physical hardware. It's not nice. So what you do, you write an emulator first. You simulate how the hardware will work, and then you make it work eventually. And then that's the other one, cross-platform solutions. It's always a nice thing. I mean, you get stuff, games. Let's just be real. from one OS to another. But the main reason probably, and that's probably why many of you are here, it's just for a hobby. It's a fun project to do. It's not going to bring you any money, absolutely, but it's just out of pleasure. This 1, 2, 3, 4, 5, and 6 are the basic building blocks that we have on an emulator. So you have, first of all, to understand how the CPU works. What I mean by that is you need to understand what are the opcodes, which are the operations, okay, that are supported by your CPU, how many you have, and what do they do. So that's the first step. The second step is the memory model, okay? Older hardware was, of course, very simple. We will see in this case with the CHIP-8, but you have a fixed amount of memory available, especially, that is especially true on very old hardware. Okay, so how much RAM do you have at your disposal? Can I write to it in every location or not? Same thing goes for registers. Timers are slightly different, somewhat of a special situation. And then you get the way you interact with it. So it's input and graphic output. Input handling can be keyboard, and maybe some of you know, but there used to be like console that had the old phone like rotator as an input mechanism. It was pretty wild. And well, clock cycles, it's actually falling into the timer, so I don't know why it's there, but yeah, anyway, I think you got it. Why they're important, though, let me mention that, is because let's say that we want to play Tetris for the Game Boy on that laptop, for example. If you don't pay attention to clock cycles, it's just not going to be playable because it's going to be too fast. And so you need to slow down your code. I mean, it's funny because you're basically writing code that will run slower, while instead we try to do the opposite usually, at least on purpose. So why will we do a CHIP-8? First of all, CHIP-8 has more or less the same structure that I mentioned to you before, those building blocks, but the architecture is very, very, very simple. It's great for beginners because you can implement it probably in an afternoon, and you will see the results immediately. One drawback of working on emulation is that you won't see the results till you're done. You need to complete the entire implementation, and then maybe you can see the results if you didn't mess anything. Testing is awkward, but it can be done. Now, the CHIP-8, for example, has 35 instructions. So it's reasonable. The next step, it's probably the 8080, the one that was used in 1978 or 9-ish to build Space Invaders, for example. It's fun, very fun. I mean, classic games, Pong. So, a bit of history. People actually used to work on these things. They actually made work on this thing. Okay, they made a living. Those are personal-ish computers, pretty heavy. One is Cosmac, as you can see. The other one is called Telmac. Why am I showing you this? Because there was this dude in 1978 called Joseph Becker, something like that. That he wanted to do like a competition and figured out a way to get people into programming, but in an easy fashion, and built something that was supposed to be easier than BASIC, for example. So he came up with CHIP-8. Now, CHIP-8 doesn't actually exist. It's not a physical hardware. It's probably one of the first virtual machines that you can see in history. It's an interpreted language, so to speak, but it's interpreted in a way that you are simulating. There we go, an entire hardware. Yeah, this is where it was born, and then during the 90s, it grew up, came back again on the HP, on the calculators. Some crazy people just decided to do another implementation on those. It's a revamp. Now, do you know what that means? Slavic. It's here be dragons. Okay, so I wanna make sure that from this moment on you're comfortable with bytes, bits, and everything, accentuation and everything else. So raise your hand if you know what a nibble is. You don't count. he implemented a CHIP-8 already, so he knows what it means. So there we go. I'm going to use this thing because I don't have a slide for that. Do you know what a byte is? Almost. There we go. Thank you, sir. So you have 1, 2, 3, 4. Step 7 and 8. This is a byte. A nibble, this, or this. High nibble, low nibble, or the opposite, depending on the NDNS that you're using. So that's it. Why I'm going to tell you this? Because we will hear the word nibble and bits, bytes a little bit during this presentation. So let's start talking about the memory layout and the actual hardware. The memory size was 4 KB. It's impressive. The amount of things that you can actually do with just that amount of money. Yes, that's a lapsus. I know. So that amount of memory. Now, can any one of you tell me how many bits do you need to represent the addresses in that amount of memory? So we have the hex notation here and here, which means that every single digit there, except the 0x at the very beginning, which is just telling us this is a hex notation, it's 16-bit. So what you need is basically you have for the F, any single F is basically, come again?
4 bits.
Yeah. Yes. Yes. Okay. Yes. So I can represent 1, 0 there with this, or an F is 1, 1, 1, and 1. I have 3 of them, which means that I need another 1, 1, 1, 1, and 1. There's another 1. So there's 12 bits. That's the amount. Well, that's the address space that I have, and that's it. Why do I tell you this thing? Because we will need it afterwards. But you need to know. That's one of the things that you need to know. So in order to implement any emulator, not just the CHIP-8, any emulator, you need to understand how much memory the original hardware had at their disposal. But once you know that, you also need to be able to read and write to that memory. So you need to know the address on the location. And to do that, you need the bits. How many do I have? Because, well, I'll tell you later. Now, that amount of memory is divided into first part, where you have the interpreter. You can think of it as the OS, the code that lets the machine run the boot operation, or you also store the fonts in there. And then anything else, that impressive amount of memory is the program space, your games, your anything, okay? Now, once we have the memory, we have the registers. You can think of the registers more or less like variables that you put into another quick access location, okay? You can immediately read or write to it. We have 16, they're 8 bits. Now, that's the 12 bits. That's the index register. This is truly extremely important because this is what stores the location or the address of the memory that we are processing during that moment. Then we have the program counter. The program counter tells us where we are on the execution. It's more or less the line number, okay, in your source code. That's what we are running right now. Which operation are we running right now? That's at line 62. That's the program counter that holds that information. And then we have the stack and the stack pointer that go together. The stack is basically a stack of the subroutine calls, method calls. We keep them, we push them into a stack. It tells us where we were before and which method we were before. And then we have a pointer that tells more or less where we are. This is, again, this is not just for the CHIP-8. This is generic, okay? This is true for every emulator. It's just with the CHIP-8 is easier. We have less. So the display, it's a funny one. It's monochrome pixels, so you cannot do anything crazy with it. It's either on or it's not. Okay, on and off. No gray, not even grayscale. Okay. If you want colors, you better get a black and green screen. That's the fanciest thing that you can get. I had one; it was great. Now the drawing method, it's funny because you do a XOR. You know how XOR works? Please tell me you do. I don't want to do it on whiteboard. I'm gonna mess it up. So the way it works is that if you have a sprite on the screen and it's moving, you're basically sending the sprite again, and that will shut it off. Okay, that's mostly it. Now, a funny story about this drawing method is that since the hardware at their disposal at the time for those programmers, they were genius, was not a lot. So you literally have to squeeze everything out of the hardware. They were mixing the presentation with the logic, which is a big no-no these days. You don't do that. But they were doing it because they had like not a lot of resources. So where I'm getting with this is that they were using this XOR-based mechanism to detect collisions. If I'm turning off a pixel that was on before, that something collided. And yeah, let me put a flag on. And then basically they were setting the VF register, which is the last one, to 1. And that's basically used for several operations, collisions included, or the carry for mathematical operations and so on. Now, then you have timers and the keypads. The keypad, it's easy. You just have 16 keys. So that was also very easy to represent. And yeah, it's a numerical plus A to F keypad, ideally, that we have to map somehow and represent somehow in our actual hardware. Timers, we had 2. They both run at 60 Hertz. And the sound timer is the only one we can only set. Okay, we don't read it because then there's something else that happens. And basically, the sound timer, when it's set, it will beep. That's it. There's no music. There is no modulation. You get, that's it. That's the only sound that you can get. Easy peasy. But if you don't learn how to crawl, you cannot run. Now, let's go into the funny part. 2 bytes per opcode, big engine. So as I told you before, you have 35 opcodes in total, which is, again, very, very approachable. The opcodes are divided into category based on the high nibble. There you go. So the way the emulator will work is that loads the ROM that you want to use during that moment, sets the program counter at 0x200, which was the start, as I mentioned before, the start location of the program, and then you move forwards. Okay, 2 bytes at a time. You read one opcode. The opcode contains both the instruction and the data the instruction has to work on. We will see that in a second. So you read those, you combine everything, you parse it, and then you execute it. And then, boom, you move forward. That's it. That's it. Or maybe you move back because the instruction is telling so. It's like playing one of those card games where every card tells a different rule. You can jump. That's the way they were calling functions. Exactly. Thank you. So this is the structure of an operation code. You have the set, which is basically the category. And then some operations, I hardly see this one used. There's 3 references. But you have others that are used more. So this is the rest of the bytes that you have at your disposal, bits that you have at your disposal, and then maybe there's even less because you don't care about some of them. let's go through a practical example. That's the binary representation of this clear to screen instruction. So the first part, okay, the 0 at the very beginning tells me the category of the opcodes. That's basically screen-related stuff, more or less. Now, the last part, the E0, tells me, okay, we are in that category, but what do? We clear the screen. Fantastic. So at this point, we take the video buffer, wipe it out. That's it. Easy peasy. Nothing else. That's the typical case. Another case, no. You jump to a subroutine located at this address. And guess what? That's 12. Okay? So this is why it's important. So the set is 0x2, which is represented by 0010 in binary, of course. And then, okay, it's a call, subroutine. We are jumping. Where? Next 12 bits. There we go. So what we do, we take the current location, the program counter, push it onto the stack, because we got to go back at some point in time, hopefully. And then we move wherever is this thing or whatever we need to do at that point. When that is done, guess what? We have the reverse, a pop operation, which is taking whatever we had on the stack before, and we go back there. We are almost done. I promise. So this is a simplified version, but it's just the core. It's literally the core of what we have. And there's multiple ways of skinning the cat. So basically the core is in this class, the instructions, but you can move those that class directly into the CPU. That's as you prefer. For easiness of writing the code, you can use a massive switch statement, which for 35 instruction is doable. It's totally doable. But in the case that then you want to take this emulator and write a different one using the same engine, that becomes unmaintainable. Again, the 8080 had 250 instructions. That starts to become a little bit awkward. So in the code that I will show you in a bit, I moved everything into the instructions, and then I have pointers to those functions. So there's literally a dictionary, a key value pair, with the set of the opcode or the opcode instruction, whatever it is, that points to the function. Cleaner. Then I've wrapped everything that tells me the state, so the clock, the memory, the registers, and the video buffer. So anything that I can read or write to into a state class, just to avoid moving around too many objects at the same time. And then this is what we are going to abstract. The sound player, which again is fabulous, great. The display, which is something already. Now, the input is the one that I didn't use an interface for, because, well, highly depends on the platform that you're writing this emulator for. So we'll see. We'll see in the code. We'll see in the code. This is how I felt when I was writing that thing. Now, what do we have? Demo time. Oh, already. Wow. So, yes. So let me see. The CPU, again, it's very, very, very simple. That's it. Less than 30 lines of code. And this is C#, so it's slightly bloated. But so what we do is every time we decide to do something at whatever frame count we want to run it, we call an update. And then there's the clock that actually takes care of, okay, maybe you're updating me to too many times per second. I'm going to slow you down. The clock takes care of that. There's an accumulation happening in it that will decide when it's time to execute the current instruction. What I want to show you, though, is, let me start with the, no, what was that? The inputs. So the input, I didn't think about implementing an interface here, because what I want is just to set a key when it's pressed or when it's not pressed anymore. And that's it. Now, I also, in some cases, I also need to get the least recently pressed key, most recent pressed key. So that's why I have that. I'm using LRU cache in this case, which expires after a little bit. So it just drops the keys. You know what? Why don't we play something? It's gonna work or not? I don't know. Well, the build field worked. Oh, it's on this screen. Yay! Now there is sound. There is sound. Well, let me see. No, that's outside. Well, anyway. Now, yeah, okay, it works. But there's also a Blazor version of it. Why am I doing this? Because that's the key point. The emulation is completely abstracted. Okay, so by using those interfaces with the display here that acts on the video buffer and the sound player, which was working, trust me. Again, there is no frequency. Okay, with the note basically that we are playing is just how long we decide to play it. When it comes to, for example, one of the most important things, the memory and the video buffer, that's it. That's how it is. Okay, it's inside a separate class just to make sure that we are communicating the behavior of it properly. So that is called, if you were to use a byte array directly, it was called primitive obsession. That's it. What's that data? What's the meaning for that data? I don't know. But now that I encapsulate it into a memory class, okay, that's my memory state. And the same thing goes for the video buffer. But in this case, I'm using Booleans, which actually not just 1 bit in C#, but that's okay. That represents the matrix of my screen, and of course I can clear it. Now, one thing that I want to mention is this reset method here. It's marked as internal. Why? Because all those classes are exposed through a state. So I have the registers, the memory, the video buffer, the clock here. But when I'm loading a ROM, this is public because that's what I'm doing from the outside. By outside, I mean what is actually representing my presentation state. Blazor, MonoGame, that's the version that you saw before. And I'm just signaling to whoever dev is going to make the implementation, me, that you are not allowed to clean only the memory, okay, or just the registers, because at this point you're going to get very bad results. So you're loading a ROM. When you're loading the ROM, you need to do all of those operations. So I'm gonna shield and prevent that you make any silly mistake. And I think we're in time. So questions, if you have them. Okay, that's great. We'll leave them for later. Thank you.
With that instruction set,
Yes.
Are there different number of clock cycles per instruction, or is it just like one?
Excellent question. This emulator does not, because it doesn't need the CHIP-8 does not need that. But that's an excellent question. Yes, other hardware has that need to slow down or make the execution run faster. But normally that is also done by modifying the position of the program counter. So that's usually what happens. Normally, though, this is an exception to the rule, because you want your hardware to run on a deterministic fashion. So it has to run at that clock cycle, and that's it. I hope that answered your question. Great. Yeah.
So the ROM, for instance, for the pong game is just a binary file?
It is. Yes, sir. Yes.
If I write one, well, and that's where I see if it works at the end, and you connect.
Correct.
It looks like it doesn't work.
It doesn't show up. You see nothing.
Okay.
That, or you see garbage. That's it, because you're just seeing random stuff. Or maybe you see an exception and the emulator just blows up because you're accessing a memory location, an address that it's wider. So let me go back to one thing. This is an excellent question because it opens, where's my mouse? It opens a different kind of world. So if I go in the opcode here, no, actually, yeah. What was that? No, it's not here. Sorry, it's not the opcode. It's in the registers. This I here is the address. Now I'm using use short, okay, because I don't need negative numbers. I don't want negativity in my life, not even in my code. So I'm using an unsigned, but that's 16 bits. That's more than I need. Now, in this case, this is primitive obsession, okay? I should not use a use short. I'm using it for simplicity, otherwise the code becomes too bloated and complex and might even slow down. But the right way would be to implement a separate data structure to represent only 12 bits. Of course, C# doesn't have it, so we're gonna live with that. But ROM is literally just a sequence of bits that you can load via a stream and pass it there and set the program counter at the 200x and let it go. That's it. You set the program counter, yes, and you let it go. Yes. It will parse the first instruction that you have at 200. What do I do? What do you do? I don't know, depends. It goes into the CPU, gets the opcode as being parsed, and then come on, you have, really? I don't even know there was a thing. You have, yeah, this is just the map of instructions. This very nice list. A little bit more than 35, but yeah. So it takes the opcode and then using that map tells me what to do. That's the CPU. Yes.
The ROM side has, does it have some kind of signature?
That's ahead of the time. It would have been. No, it was too early in time probably to get filed,
Okay.
signed. You know, it was. You're worried about your hardware being cracked and information stolen and everything else. No.
Get it from somewhere. It's made for this CHIP-8.
Yes, sir. Yes. You hope it works. If it doesn't work, maybe you made a mistake with your emulator. That's it.
You could download it from a VDS.
Also, yes. Yeah, that's it. But no, it has to be specific for the CHIP-8. Imagine that, I don't know, a long time ago, you had PC, they were just rising, and then at the same time, you had the Amiga, the Commodore Amiga. There was, oh my God, you can do music on this thing. You can do, I don't know, video games. That's excellent. Try taking a floppy disk from the Amiga running into the PC. It doesn't work. That's the same thing if you take a package meant for Mac OS, Linux, and you try to run on the Windows. It doesn't work. Yeah, let's go. Yes. No, there's already available. Yes, you can find them online already. We'll have been fun though. Thank you. You gave me something to do this night. But it's doable. It's totally doable. Yes. Now testing. Probably this instruction file is the only one that you want to test. Yes. Yeah. You can do unit tests with that. Just sending the opcode to the right instruction, and you expect values. You check the contents of the video buffer or of the registers. You know, the goal is that you don't write to the memory because that's loaded from the ROM, so it's a ROM. Okay, but you write to the registers. So you execute an instruction, and then you check the registers, and then you make your assertions. OK, this is what I want. And then you move forwards. And that's it.
You could write containering language.
Yeah, of course. Yes. Anything. I mean, I use C# because I love it, but you can use whatever. You can use assembly if you're crazy enough. Who's next?
Could you show like how you did like list addition instruction? Like,
What do you mean?
You implemented the add instruction.
Oh, yeah, the add instruction. OK. Let me figure that. I don't know. So there we go. That's it. You want me to explain it, or sure? Okay. I don't remember. Yeah, no, that's. I actually wrote this thing 3 years ago. Okay, so bear with me. I'm just going through the code. So you take the opcode at this point. I guess it takes the last 8 bits here. So that's the NN. So we take whatever. Oh yeah, I forgot to mention. There's also X and Y, which are other locations in the bits that you have at your disposal, okay, on the opcode. So it takes whatever is in this register, okay, indicated by the X, and it adds whatever it's in the parameter that we have on the opcode. We might get some carry, so we handle that that way, and then we store the result in the same register that we had before. Now I'm using a mask here because, of course, that might be very well a memory location afterwards. So we need to make sure that we are not having any overflow, for example. Thank you.
Thank you very much, David.
Thank you for coming. Thanks.